Introduce our principal speaker, Mladen Bestvina. I first met Mladen back in 1988 when we were both first-year graduate students at the University of Tennessee. Mladen didn't stick around very long, but in less than 2 years, he had aced all his prelims, written a knockout dissertation, and gotten a tenure track offer at one of the top 10 departments in the country. Took me a little bit longer, but you know what? The great thing about Mladen coming and making a big splash like that is he's gone on and continued to do great things ever since then. So I always like to brag about that connection, and it's fun to have him come back and give a talk, or come back to this workshop. Not specifically in Milwaukee, but Mladen was once before the principal speaker at this conference, and that was a big success. So we're really happy to have him again. Mladen Bestvina.
Thank you. Thank you for the invitation. I haven't quite decided what to do on the third talk, but the first two talks will be very closely related. And I'll start by talking about PL Morse theory. So let's first review a little bit of the usual smooth Morse theory. Just a 5-minute review. Is this loud enough?
What?
Okay.
Yeah, I think you should
Speak louder?
use the mic.
Okay, talk louder. Okay, I'll try talking louder. Okay, smooth Morse theory. Although in my calculus class I would tell the back row to move up. Okay, smooth Morse theory. Okay, so the setting is you have a smooth manifold and you have a function, also smooth. And then you say that a point P in M is critical if the derivative at that point is 0. That is, in local coordinates, all partials are 0. Okay, and then you say that this critical point is non-degenerate. If when you form the matrix of second partials, so-called the Hessian, that matrix is non-singular. So you look at this matrix in local coordinates, and you require that the determinant is non-zero, that this matrix is non-degenerate. Okay, and that doesn't depend on the choice of the local coordinates. And then the function f is called Morse if every critical point is non-degenerate. F is Morse if every critical point is non-degenerate. Okay. And then there's the key lemma, which is called the Morse lemma. And that is that at a non-degenerate critical point, the function is standard. In suitable local coordinates, there's only really one function for every number between 0 and n. So the Morse lemma is that, so let P in M be a non-degenerate critical point. Then in suitable local coordinates, the function, and in these coordinates, P is 0. Okay? P is the origin. The function can be written as f of x1 through xn. These are the local coordinates. This is just some constant, and then you have a quadratic function, minus x1 squared, minus x2 squared, and so on. There are lambda negative signs, and then the other signs are positive. Okay? And furthermore, this number lambda does not depend on the choice of the suitable local coordinates. You could choose local coordinates in different ways where the function has this form, but this number lambda doesn't depend on which ones you choose. Okay? And so lambda is well defined and is called the index. It's called the index of P. Okay. And usually one imposes conditions like function should be proper and bounded from below. And in that setting, there's maybe the main theorem of Morse theory is that if f from M is Morse proper, then M is homotopy equivalent to a CW complex, where you have one cell for every critical point of F, and the dimension of that cell is equal to the index. Okay, so then M is homotopy equivalent to X, and X is a CW complex, and there's a cell in X for every critical point of F, and the dimension is equal to the index. Okay, so the standard example that everybody has to know when they talk about Morse theory is the torus. So you think about a round torus, a donut, that just is positioned in 3 space like this, and you look at the function, which is the height function, the z coordinate. And then there are 4 critical points. There's one at the bottom, that's the minimum. There's the maximum, and then there are 2 saddle points. So this is index 0, index 2, and this is 1. That is locally, at the saddle point, the function looks like x squared minus y squared. And here it looks like x squared plus y squared. There are 0 negative signs, and here there are 2 negative signs, because here it looks like minus x squared minus y squared. And indeed, a torus is homotopy equivalent to a CW complex with 1 0 cell, 2 1 cells, and 1 2 cell. Somehow the key, the topological key in this business here is the fact that the space of, if you take a critical point of this type, then the space of descending directions is homotopy equivalent to a sphere of dimension lambda minus 1. So for example, if I take the function f of xy equals x squared minus y squared, right? Then what does this function look like? Well, of course it's 0 at the origin, and then it's going to be also 0 on these 2 lines. It's negative in these 2 regions, and it's positive in these 2 regions. So if you're standing at the origin and you're wondering in how many directions can you lead the origin in such a way that the function goes down, well, that space is homotopy equivalent to a 0 sphere. In this case, the 2 contractible components. And in general, if you take a critical point of index lambda, then the space of descending directions is homotopy equivalent to a sphere of dimension lambda minus 1. That's why this index is topologically well defined. It doesn't depend on the choice of local coordinates. Okay, so now let's talk about the PL version of this. The category, the most general category of spaces where PL Morse theory works that I know is what I call affine polyhedral or affine polytope complexes. So let's first define what an ABC is. Okay, so that's an affine polytope complex. This is going to include simplicial complexes, and it will include cube complexes, and a few other things as well. It's a CW complex whose cells are polytopes. That's basically what the definition will say. Okay, so here's a cell complex. X, where every cell, E, is equipped with a characteristic function, chi sub E. So this goes from some ball, CE, it's going to be a polyhedron, and goes into X. So that, okay, so there are 3 conditions. Let me make sure I don't forget anything. So this CE is a convex polyhedral cell. Rm or Rm. For now, I'm going to fix m. M is going to be fixed for in the whole definition. You could allow m to depend on the cell, but that'll just make things more complicated. The price to pay is that these spaces are always going to be finite dimensional, but that's not going to bother us too much. Okay, so all cells are modeled on some convex polyhedral cell. All cells are convex polyhedral cells in the Euclidean space. This chi e is an embedding. So the cell is really sitting inside X. And if you should also think of these characteristic functions as being well defined up to affine homeomorphisms of Rm. That is, if I have a characteristic function like this, I could precompose it by an affine homomorphism of the Euclidean space, and I'll get another characteristic function. You should regard them all as being equivalent. In other words, characteristic functions are defined up to precomposition by affine homomorphism. So that's what number 3 is going to say. That's just that if you restrict, so chi e restricted to a face of CE. So I take a characteristic function restricted to a face. Well, that's going to give me another characteristic function in my collection, except that it might be precomposed by an affine homomorphism. So this is a composition of another characteristic function of some other cell, composed with an affine homeo. Okay. But it's better to think of these characteristic functions as being defined up to, it's not just one function, but it's a whole family where you're allowed to precompose by a characteristic function. Then this number 3 will become simpler, and you would just say that if you restrict the characteristic function to a face, you get another characteristic function. And the basic examples are simplicial complexes. That's where all cells are simplices, obviously. And then also cube complexes. And that's where you glue a bunch of cubes together along their faces. But you could do other things. You could do pentagons, for example, or whatever you want. Okay. And in this definition, as I said, X is always finite dimensional because everything is sitting inside this Rm. But you could allow M to depend on the cell, and then just include Rm into Rm plus 1 in the standard way. Okay, let's not worry about that. Okay, so now I want to define Mladen Morse functions in such an object. So definition. So let X be ABC. Okay. And let F be, so F is going to be a function. F from X to R is Morse function. Okay. Okay, so again there are 3 conditions. The first one will say that when you restrict this function to any cell, you get an affine function. Okay, and that makes sense because these cells are given an affine structure. So technically, what we say is that when you compose f with a characteristic function, right, you do a characteristic function containing f. So that's a map from this polyhedron CE to R. I want that to extend to an affine function from Rm. Affine it's linear, but 0 doesn't have to go to 0, right? So it's just a linear function plus a constant. That's what affine is.
Mladen, is polyhedral cell is the convex whole of finite manifold.
Yes. The second condition will say that the vertices are the only critical points. That is, if you take an edge, it's not horizontal with respect to this function. So in other words, if you restrict, if f restricted to a cell is constant, that implies that E is a vertex. The dimension of E is 0. So edges are not horizontal with respect to this function. Now notice that because of our ability to change characteristic functions by precomposing with affine homomorphisms, number one really says that you can imagine that on every cell, the function is just a height function. You can reposition your cell so that by an affine homomorphism, so that this function restricted to it is just a height function. That's really what one is saying. And two, I mean, it's not a constant function; it's a height function. And then number three, this is somehow what replaces properness. I want the image of the vertices to be a discrete set. So I have a zero scale R to be discrete. Okay, that's the definition. And here's then a sample lemma. Oh, first notice also that if X is a simplicial complex, then this condition 1 becomes fairly simple. It just says that so if X is a simplicial complex, then number 1 is really equivalent to saying that the function is determined by the values on its vertices, on the vertices of the complex. So you know, I mean, very similar coordinates. You take a linear, you take a convex combination of the vertices to get the point in the general simplex. Well, that should be the same as the, you know, that's what one says. The function is determined by what it does in the vertices. Okay, so that's the official one.
One. Yeah. Does 3 allow vertices, 2 vertices to have the same height?
Yes, it does. Okay, so here's the first proposition. So let's suppose that we have an interval. So J is going to be a closed interval A, B, in R. And I'm going to assume that that this half open interval A, B, so excluding A, that does not intersect the image of the vertex. Then the point is that, so in Morse theory, of course, you're imagining you want to compare the homotopy type of the sublevel sets at A and the sublevel sets at B. Well, this proposition says that they're the same. Nothing homotopically, nothing happens as you go from A to B. Okay, so then you know, F inverse of J is going to deformation reject F inverse of A. Okay, so the picture is, well, I guess I'm tempted to draw a smooth picture. This is really the case when you don't have any critical point between A and B. And so here's my function, and I'm considering 2 values, A and B, so that between these 2 values there are no critical points. This is my F inverse of J. And the claim is that you can deformation reject F inverse of J down to the A level. And in particular, you can glue on everything that's below A, and that's going to say that the corollary is that F inverse of minus infinity B is homotopy equivalent to F inverse of minus infinity A. And that's what you really should be thinking about. So I'm filling up my space with water, starting from minus infinity and going over to plus infinity. And I'm interested in knowing what happens, at what moments the homotopy type changes. Well, it doesn't change as you go from A to B. That's what this proposition is saying. And it's somehow due to the fact that there are no critical points between A. Okay, and the proof is really simple. Let me just sketch what it is. You define AI. This is going to be F inverse of A union the intersection of F inverse of J with the I skeleton. Well, okay, so the picture is coming, but the idea is now that f inverse of A is really A minus 1. And then this is kind of an increasing collection of spaces ending with AM, and AM is f inverse of A. Okay. And what I'm claiming is that each of these AI's deformation retracts to the previous. So the claim is that AI plus 1 deformation retracts to AI for all I. So that by composing these, you get the deformation retraction. And what is the picture? Well, here I want to draw the picture just on a restricted to one of the cells. So, so maybe the cell looks like a square, and I want to position the cell so that the function restricted to it is the height function. Okay, so f is the height function here, and I'm allowed to do this. Okay, and then you have your levels A and B, and between A and B there are no vertices. So if you look at the pre-image, then you see, in this case, you see another convex polyhedral cell if you want. And it's this is it. This is f inverse of. Well, in fact, this is A2. This belongs to A2 in this picture, right? And what is A1 in this picture? Well, it's this. This is A1. And I'm claiming that A2 deformation reducts to A1. And the proof is obvious, right? You just position a point above this object here, and you can do this because there are no vertices over here on this top edge. You wouldn't be able to do this if there was a vertex here. But you just go up a little bit, and then you project, radially project, and that gives you deformation retraction from A2 to A1, and you do this cell by cell. You look at, when you're proving this, you look at all I plus 1 cells that intersect f inverse of J, and you do this separately on each such cell. And you compose until you get down to f inverse of A. Okay, that's it. Okay, so what happens at the vertices? What if we have vertices between A and B? How does the homotopy type change? So we have to talk about descending directions, just like in smooth Morse theory. So here's the definition. So let's fix B, a vertex in X. Okay, I'm going to say that a cell is descending if it contains this vertex B, and B is the highest vertex that the cell contains. Okay, so cell E in X is descending. This is all with respect to B. If B is a vertex in E, and W in E implies W vertex in E implies that f of W is less than B. So B is the highest vertex. So here's an example. I want to look at maybe a complex like this. Well, let's say here's a hexagon, a solid hexagon, so that's triangulated in this way, and f is the height function, and here's vertex B. So what are the cells that are descending at B? Well, they're these two triangles. Because B is the highest vertex in these triangles. It's not, this is not a descending triangle because there is a higher vertex. And obviously these will be called ascending. These two triangles will be ascending. So similarly ascending. Okay, so there are two descending and two ascending triangles. And now I want to define the descending link. And this is somehow the space of descending directions. And how many ways can you go down homotopically? Well, what matters is the descending cells. These cells that are not descending, like this one here, there are some descending directions there, but that's always going to deformation reject down because half the directions here are descending and half are ascending, but you can deformation reject the descending directions down to the descending cells. So the descending link function is understood. This is just, I take the link of B in the union of the descending cells. So union of E, where B is in E and E is descending. Okay. Take the union of all descending cells as B, and then take the link in that union. So in this case, you will get just an arc, triangulated. This is the descending link. Okay. Another example is the monkey saddle. This is what doesn't happen in the smooth case. Okay, so another example. Suppose I have the same space, but I'm going to look at the function that sends, so here's my space, the disk triangulated as before, but I'm going to send this middle vertex to 0, and I'll send these other vertices to 1 and -1, alternating fashion. Okay. So then what is the descending link at 0? Well, it consists of, the descending cells are these 3 edges. Here's 1, 2, 3. So the descending link consists of 3 points. Right? The descending link is 3 points. Okay. It's not a sphere. So in the PL world, there is no reason to expect that descending links are spheres like in smooth case. They can be just about any finite complex, or infinite if your space is not local. Okay, and then there's a description of how the homotopy type changes as you pass through a vertex like this. And what happens is that you have to cone off the descending link. Just like in the smooth case, where the descending link was always a sphere, so you are also adding a cell, attaching a cell. Well, here, you just have to cone off whatever the descending link is. So, the proposition is, for simplicity, I'm going to state it as if there's only one vertex that maps into the interval that we're considering. But this is, the same is true with the marriage. So, J again is AB, and F inverse of J contains one vertex, B, and in addition, this vertex maps to B. Okay, so it's at the top of my interval. So I'm interested in knowing what happens when the water level reaches B. How does that homotopy type change? Okay, then F inverse of minus infinity B is homotopy equivalent to F inverse of minus infinity A with a copy of the descending link B coned off. Okay, maybe an example. Well, here's a silly example. We just take this graph, letter X. It's a graph, and the height function. And here's a vertex. The descending link contains 2 points. And so what happens? How do how does the homotopy type change as you go from, here's maybe B, here's A. How does the homotopy type change as you move from B to A? Well, at B, the preimage contained, the green set is the sublevel set at B. And at A, it's of course calling this interval. The two green bits connect up. And the reason that they did so was that we had to attach the two green bits, the cone on 2 points. And the cone on 2 points is an arc. So we attach an arc with one endpoint here and the other. And that became the red set. Well, okay, I don't want to write down a detailed proof, but it is very similar to the one over there, with just one little change. We don't do these deformation retractions on the descending cells. We just skip the descending cells. Okay, so to get to the proof is we define so if E is a descending cell, define a set SE. SE is going to be this E intersect F inverse of J. So this is the part of this set that we're interested in that moves in the cell. And what is that set? Well, we see it's a, so here's a descending cell, and here's B, here's, sorry, I guess I switched A and B. B is supposed to be higher than B. Okay, so here's A. So this is the set SE, right? And this set is really the cone on. This is the cone on the link of V and E. Okay, and this link of V and E is something that makes up the descending link. It's part of the descending link. The descending link was defined as the union of these links. And so you define now, AI. This is going to be not just F inverse of. Sorry. Let's start with A minus 1. A minus 1 is going to be F inverse of A union these SEs for all cells that are descending. And that's F inverse of A with the, so this is F inverse of A with cone on, with the descending link coned up. And then you define AI to be A minus 1 union, just like before. Union F inverse of J intersect XI. Okay, just add in the I skeleton above this F inverse of J. And then you have this sequence of inclusions as before. AM is just equal to F inverse of J. This is equal to what I just said. That's this. F inverse made with the links called up. And you show in this exactly the same way that you have deformation retractions from AI plus 1, deformation matrix to AI. Simply we just skipped the cells that were descending. Because there we don't know how to do this. We don't have a vertex that we can put above the level set. So we just skip it. We just leave them there. And the price to pay is that at the end, we're not left with F inverse of A, but we're left with also with these sets SC. They form exactly the column in the center. And that's it. But what makes Morse theory interesting is not so much how you exactly pin down every detail of this argument, but the applications. And that's what I was going to spend most of my time on. Also in practice, one has to tinker with this theory a little bit. It's usually some assumption will not hold. Maybe Maybe the number 3 is not detailed a lot. The image of your vertex set might not be discrete. Then you have to come up with some additional tricks. Actually, in the first, is that the first example? Yeah, the first example I will do, the codomain for the function is not going to be R. Okay, that also sounds bad. But in fact, in this example, it'll be easy to fix. It'll be just some ordered set, but at least as I defined it for the vertex set. Okay, so let's get on with the example. Are there any questions? Is this clear? Somehow the descending link is a fundamental concept here. So if it's not clear, ask. Okay. So this is really an excuse for me to introduce some of the basic spaces in geometric. And the first one I want to talk about is the, to use a fancy name, it's a building associated with SLN. So in geometric group theory, one likes to have spaces in which your favorite group acts. And so suppose you want to study, SLN Z, say. Then you want a nice space where this group acts. And this building is such a space. Okay, so I want to talk about the Solomon theorem. So this the definition is kind of algebraic. So you start with the field. If K is going to be any field. For example, finite. If you want to draw pictures, then it better be finite. And then we want to define the space X. This is going to be the associated. It's a simplicial complex. It's a simplicial complex, and the vertices I should also say we fix a number n. So k to the nth power of k. This is a vector space. This is a vector space over k. So we're going to define the simplicial complex. The vertices are proper subspaces, linear subspaces of k. Proper means not 0 and not all of kn. So the dimension has to be between 1 and n minus 1.
Yeah. Kn then?
Kn. This is kn. That's
no,
all right.
No, proper subspaces.
Oh, kn. Yes, thank you. Okay, and then what's a simplex? Well, a simplex corresponds to a flag. That is to a chain of inclusions of proper subspaces. Simplices, these are chains. Okay, so what's an example? You can't really draw too many pictures here, but let's say k is q. Maybe this is the most important example for us. Then let's say n is 2. Okay. Then this is kind of silly because proper subspace is a line. There's no other, right? Only line is a proper subspace. So in this case, X is going to be a discrete set. You'll have one point for every line. So it's kind of it's a projective space, projective plane, projective line, but the discrete topology. Right? What if k is q, but n is 3? But I mean, q doesn't really play much of a role. And if n is 3, then I have two kinds of subspaces. I have lines and I have planes. So I can imagine drawing all the lines over here on the left side of the board. And so I have some kind of a discrete set, one for every line. And then over here I have planes, one point for every plane. when do I draw an edge between a line and a plane? Well, if that line is contained in the plane. Okay? So we have, so of course every line is contained in infinitely many planes, and every plane contains infinitely many lines. So this is going to be kind of a nasty looking graph. It's a bipartite graph, but every vertex is infinite valence. Okay, that's what the space looks like. Also notice that there are distinguished hexagons here. That is, if I choose a basis for my space, so let's say E1, E2, E3 basis. Okay, Q. Then I have a natural hexagon. Then hexagon. Let's count. This is 1, 2, 3, 4, 5, 6. Okay, so there's a span of E1 that represents a line, span of E2, span of E3. And then there's a span of E1 and E3 that's a plane. Span of E2 and E3 is a plane. E1, E2 is a plane. Okay, so this is a subgraph, subcomplex. So such hexagons are called apartments. This all generalizes to higher dimensions as well. This apartment is always going to be a subdivided, pericentrically subdivided boundary of a simplex. Okay? If I take if n is equal to 4, then the apartment is going to look like this. It will be so n equals 4. The apartment is a subdivided simplex. So the vertices will correspond to lines E1, E2, E3, E4, and then there are various verticenters. Each verticenter corresponds to a subspace. For example, this verticenter here on this edge corresponds to the span of E1 and E3. And the vericenter of a face will correspond to a three-dimensional subspace. So these naturally sit inside like complex X. And this satisfies various nice axioms. One can define buildings axiomatically, and they exist for arithmetic groups. Every arithmetic group has a building. But the main theorem about this is that the homotopy type of the building associated, say, with SLN is a wedge of spheres. Okay, so that's the Solomon-Fitts theorem. So X is homotopy equivalent to wedge n minus 2 spheres. Of course, if the field K is infinite, then we'll have infinitely many spheres and wedge. If K is finite, we'll have finitely many spheres. And you can, as an exercise, you can try to count how many spheres there are if the case of a finite field. Okay, so let's prove this using Morse theory. So X is a simplicial complex. To define a Morse function on a simplicial complex, I just have to tell you where to send the vertices. And then that little formula about the pericentric coordinates tells you vertices. Okay, so this is going to be induction of n. If n is equal to 2, then there is nothing to do. It's just a discrete set, and that's the way to zero sphere. Okay, so let's fix some n. Fix n variables. And I want to define my function. So the function will depend on the choice of the line. So I want to arbitrarily fix one of the lines in my space. So let L in Kn be a one-dimensional subspace. And now I'm going to define the function. Now, unfortunately, the function will not go into R. It will go into an ordered set, which can be embedded in R. So define f from the vertex set of x into the following product, ordered lexical capital. So this is this one and next one. It's a finite set, ordered lexical capital. That's really what Morse theory wants you to have. The target should be somehow ordered, so that you know in which order to go to the water. It doesn't really have to be hard. Okay, so what is this function? So the second coordinate is just going to be the dimension. So the vertex really is represented by proper subspace, right? So I have to tell you where to send the proper subspace. The second coordinate will just be the dimension of that subspace. And the first coordinate will be either 0 or 1, depending on whether this subspace contains our favorite line or not. Okay, so P is my proper subspace. This is going to be equal to A dimension of P. And A is 0 if L is in the subspace, and it's 1 if L is not in the subspace. Okay, so I'm adding these vertices, so these proper subspaces according to their dimension, but I first want to do the ones that contain L, and then the rest. Okay, so what's the discussion of descending links here? So the absolute minimum. Okay, so the descending link is of P is going to be empty if P is L. This corresponds to the absolute minimum. What's the minimum value of the function? Well, it's 0, 1, right? Where A is 0 and then the dimension is 1. That corresponds to the line L. And nobody else is, well, as we'll see, nobody else is the empty descending. It's clear that this is the absolute minimum. The only absolute minimum. Okay. Now let's say that A is, so if A is equal to 0 and P is not equal to 1, so what happens then? So now I have a proper subspace that's not one-dimensional, but it contains L. Okay, then what is the descending link? Well, I have to find a subspace that's either contained in P or contains P. But the first coordinate, if I'm going to be descending, the first coordinate has to be 0. Okay, so that subspace has to contain L. And the second coordinate is not allowed to be bigger than the dimension of P. It has to be smaller. So in other words, the descending link just consists of proper subspaces of P that happen to contain L. Right? So then the descending link is proper subspaces P that contain L. Right? Nobody else makes it into the descending link, because either it's not in the link at all, or it's not descending, or the value is higher. But what is that? That's a cone, because L is a component. Everybody in this collection contains L. So L plays the role of a component. So it's a component on L. L is a component. L is a component. So it's contractible. Okay, that's important. When the descending link is contractible, then the homotopy type doesn't change, right? Because you're coning off something contractible. That's not going to change the homotopy. Okay, so what happens if A is equal to 1 and the dimension of P, so we have to consider a case when the dimension of P is strictly less than n minus 1. Okay, so how can I, so again, to be in the link, I have to be either contained in P or I have to contain P. But, so which ones are going to be descending? Well, if I'm inside P, then I'm certainly descending, because the first coordinate is still going to be 1. I mean, this means that P doesn't contain L. But the dimension will be small, right? So this is the descending link is the span of So proper subspaces of P. And then how about the superspaces? What are the superspaces of P that are in the descending plane? Well, if they're going to have larger dimension, then they have to contain L. Otherwise, they're not going to be descending. So in other words, so N superspaces, what? They have to contain both P and L. So it's a span of P union L. You take the span of P union L, and here's the P, here's L, and you take the span, and that's a subspace of one dimension higher, and it's proper, because we're assuming the dimension of P is less than 1. And anybody, so that subspace, this span of P union L is in the descending plane, and anybody that contains it. But the point is that's also a cone on this guy here. It's also a cone. Right? And that's a cone. The span of P union L is a cone. And then finally, when A is equal to 1, and the dimension of P is equal to N minus 1, then we can't make this span P union L. P is already a maximal dimension. There's no way to go on. So it's just proper subspaces of P. Proper subspaces of P here. And that is the building for in one-dimensional k n minus 1. Right? P is n minus 1 dimensional here. So it's an n minus 1 dimensional space, and we're considering all proper subspaces of this one n minus 1 dimensional space. So this is homotopy equivalent by induction. By induction, this is homotopy equivalent to a wedge of n minus 3 space. And there you have it. So now Morse theory takes over. You start at the minimum, then you get the point, so it's contractible. And you keep adding water, and you pass through various vertices. All the descending lengths are contractible, so you don't change the homotopy type until you get to the very top. This is the maximum delta. 1 n minus 1 is the maximum delta. At that point, you cone off these wedges of n minus 3 spheres. If you have a contractible space, and then you cone off a subspace, which is a wedge of n minus 3 spheres, then the result is a wedge of n minus 2 spheres. And you do this several times. There are many, if k is infinite, then there are infinite to many such p. But they all live at the same level. So you do all these conings off independent of each other. And that proves it here. Okay. When did I start?
You started a quarter after.
Where are we? So about 10 minutes? Okay. Okay, so I was going to talk about the arc complex a little bit. There's this arc complex is contractible using Morse theory, which I think is really useful. Okay, so the point is that maybe you don't want to study SLN Z or something. That's very algebraic. Maybe you like that better. So what's a good space where the mapping clause go back? Well, there's a tabular space, but that's of course very analytic. And in fact, what I'm about to describe is a combinatorial version of the tabular arc complex. So we'll start with some kind of a surface. And the definition can be made completely topological. We can talk about isotopy, classes of arcs, and so on. But the proof will rely on hyperbolic geometry. So I will make the definition from the point of view of hyperbolic geometry. So S is going to be a complete hyperbolic surface. Finite area. And also totally geodesic boundary. So those are the words. Experts. Let me just give you some examples. So cusps are allowed. Okay, that's the point here. Cusps are allowed, and they can be on the boundary too. That is, you know, what basic examples are maybe I can take an ideal polygon, hyperbolic space. Here's an ideal pentagon. So, you know, a hyperbolic space, you know, including 5 vertices on the boundary and taking the convex hull. So that's an example of such a surface. You can also take something like this. Here's a torus with one cusp. We do want the surface not to be compact, otherwise you can't talk about arcs. Arcs will have to go from cusp to cusp. Okay, so then what is the arc complex? So A is going to be a simplicial complex. The vertex is going to be represented by an embedded geodesic arc whose ends are in cusps. So vertices, geodesic lines joining cusp and not containing the boundary. So for example, in the case of a polygon, you're just looking at the diagonals. It's a complex of diagonals. That's the simplest case of an arc complex. Here's a typical arc. That represents the vertex of this complex. And over here, maybe here's a typical arc. Okay? And when do I put a simplex for a collection of these? Well, if they're disjoint. Okay, so simplex in A, this corresponds to disjoint collections. So it's a simplicial complex. And the mapping clause, the group of homeomorphisms of isotropy, is acting on this. Now, if I have a homeomorphism of, say, the surface here, I can see what it does to this arc. It will send it to some other arc. It might not be geodesic, but I can homotope it to a unique geodesic arc, and that's going to be that's the action of that homeomorphism on the arc. Okay, so what are some examples? If I take now I'm going to refer to drawing the logical pictures. So here's a quadrilateral. So the arc complex here is just 2 points because it just has 2 diagonals. Right? There are 2 diagonals and they intersect. So the arc complex consists of just 2 points. If I take a pentagon, then I have a total of 5 diagonals, and they form a circle. So it's here's the arc complex. So what do you think it's going to be for a hexagon? My analogy. So here it's a 0 sphere, here's a 1 sphere. So here's another example that's a classical, but maybe less known. So I take my surface to be there. Okay, so an arc now goes from cusp to cusp. So you have if you think of the finite picture where you draw a torus with a point on it, then this arc will be represented by a simple closed curve. So the simple closed curve has a slope. And so you can, so you see that the vertices of this complex correspond to the rational numbers together with infinity. So what one usually draws is this kind of a picture. So this is the picture you get. So these are the the x-coordinates here are rational numbers, and two rational numbers are joined by an edge. So PQ and R P over Q and R over S are joined. Even only if PS minus QR. Okay, so this is called a fairy graph. It's a filled-in fairy graph. It's filled in because these triangles are also in there. You know, here I have three arcs that are pairwise adjoint, and therefore there's two symbols. Okay. Here's another example. So again, I'm going to draw a topological picture. I have a triangle, and I have a puncture in the middle. So you can draw this hyperbolically too. It's a kind of a crown picture. A hat. Custom. And if I label these vertices, say 1, 2, 3, and center, then the arc complex is the following. Triangle in the middle. Okay. So what do these represent? So I want to say this is 1, 1, 1, 2, 1, 3, 2, 2. This is 1 center, center, 3 center. Okay, so for example, 1, 1 means this. Goes from 1 to 1. You know, 1, 2 means this arc. That's the only arc that goes from 1 to 2. The edge itself is not blocked. 1C is this arc. And so if you figure out what's the joint, then these are filled in triangles. So it's a disk with this particular triangulation. Okay. And the theorem is that S is an n-log, then the arc complex is the sphere of dimension n minus 4. And otherwise, or if S doesn't have to be connected, but if S has a non-disk component, then A is contractible. And what happens is that you delete the subcomplex that's where you don't have local finiteness. See, in this picture here, for instance, this edge is fine. This edge is the complex is locally finite at any of these points. Where it fails to be locally finite is at the rational points here on this point. If you delete those vertices, then you get a contractible space which is locally finite. And it turns out it's homeomorphic to Teichner space. So it's a combinatorial way of building a Teichner space. And somehow this first part tells you that it's a manifold. Because links, if we have to, I'm running out of time, so I won't have time to explain that. But the links of points in the locally finite part can be identified with arc complexes and disks. So this first part is just telling you the lengths of points in this locally finite part are spheres, which means that what you have is a manifold. And at the locally infinite part, the links are contractible. That's also part. You can identify the link with some other arc complex, which by this theorem is contractible. And so this set where you have that you're deleting is kind of a Z set, because all the links are contractible. So when you remove that, your space is still contractible. So you have this nice contractible locally finite, not only locally finite, but it's a manifold. And then there's a theorem that says that it's in fact equivariant on the working plane. It gives you a triangulation of vectors. Okay, so my time is up. Yeah.
We do have a little extra time for this cancellation. So you want to take a few extra minutes to...
Yeah, well, so I was going to do a proof of this, and I'm guessing this will take maybe 15 minutes. That's probably not. I could reorganize my talk too and talk about this for the first 15 minutes. So whatever you want.
Our schedule can handle it. I don't know if you've exhausted it yet, but...
I don't know. Whatever people want. Should we take a break and then for those who are interested, I can do another 15 minutes or what? I'm easy.
Maybe people have questions.
Okay, should we take a pause for questions now? Is that what you're suggesting? I don't know.
People want to ask questions. I have some questions.
Go for it.
Well, I got lost at some point, and that torus with the cusp, how is that related to the fairy graph? I didn't quite get that.
So if you draw a red curve, then there's a well-defined slope. You see, I can think of this picture as being, I can draw it in, the torus in a more standard fashion like this, and then I can draw my red curve in a more standard fashion. And then there's a slope, which is a rational number. But I can fix, there's meridian and the longitude, and this curve lines up the meridian so many times, and the longitude so many times, so that gives me a slope. So I'm going to represent that curve by that rational number. Okay? And then I have to figure out when two of those are connected by an edge. Well, the claim is that if and only if this condition holds. In other words, if the slopes behave in this way. And if you think about this, that's just saying that the intersection number is, this is the intersection number. If I take two curves of slope P over Q and R over S, the intersection number is given by this. And so the intersection number has to be 1, because they intersect only kind of with the cusp. But the cusp is not really there, so the arcs are disjoint. This, as I defined it over here. So this is the condition for them to be joined by an edge. And so that's exactly the definition of fair.
I get it. Now that picture in the upper right corner, what is the triangle on the left? What's it the center?
This is the surface. This is S. S is the triangle with another puncture. So if I want to draw it hyperbolically, I'll probably draw a picture like this. Like this, and then there's a.
I see. Yeah. And hyperbolic freeze.
This is at infinity. This is the center point. It's a cusp at infinity. And then there are 3 more cusps, but they're on the boundary. Okay. And so I can think of these arcs. Topologically, they're just arcs joining the vertices, but they're not allowed to be isotopic into the boundary. Well, minus the vertices. So this arc, of course, is isotopic into the boundary, but it will cross the vertex, so that's okay. This is an essential arc. Okay.
Yeah.
And what about the one that first example, the square? I didn't exactly understand this in the middle, up at the
This
top.
one?
I didn't understand.
That's a hyperbolic square.
Well, I can draw it hyperbolically, but it's the same.
And the arcs,
The
arcs
arc,
you drew,
there are 2 arcs in this case.
but
I'm
they
looking at
do
arcs,
intersect.
one-
They do intersect, or
Yeah,
they
so that's
They
why
do
there's no one.
They do.
They do. That's why there is no edge here.
Got it.
Okay? It's a zero sphere.
Figured backwards.
It's a zero sphere. And then here it's the 1 sphere. Okay? So you can, I don't know, if you can tell me maybe.
So what do these things have to do with Morse theory over here? These are
So the proof of this is using Morse theory, but I haven't gotten to it. So I could do it tomorrow. Maybe I should do it tomorrow because it's a nice example. And it will. This is fairly simple. this theorem about n-gons, because there are only finitely many vertices in this case. But in general, in the case of the arc complex, it turns out that this will fail. This image will not be discrete. So you need an additional trick. That's I was hoping to talk about that.
So the Morse theory is used to see what these things are topologically, I guess. I mean, so you have like these hyperbolic n-gons and look at the arc complex and you want to know what it looks like, and so the Morse theory comes in to help us understand.
Yeah, so the way you prove it's a sphere is you fill it with water.
Well, I feel better now because I thought I was supposed to see it after you.
No. I haven't gotten to the proof yet.
Okay.
The proof might come tomorrow.
Okay.
Or maybe later, I don't know. Later, I don't care. Whatever people want.
And what was the statement again? That if there's any non-disk component,
Then it's contracted.
does that include this triangle, this last example?
Yeah, for example. It's finite in this case, but it is still contracted. It is.
Oh, it's the same, right?
Yeah.
Mladen, just out of curiosity, I mean, people must have thought about PL Morse theory before, but has anybody done anything with it? I mean, Jaco seems to take all these things in one category and change it to another category, but what you got here is some application.
Well, this is, I mean, I really think of this as being folklore. I mean, people have known this probably. Euler probably knows.
He knew everything, right?
So there's Foreman at Rice. He also has kind of a Morse theory, but it's a little bit different. He wants to generalize the idea of a gradient flow. So there is some notion of a gradient flow in the PL world.
But you came into this from geometric group theory because you had these things and you wanted to understand them, and so that's
Yeah. So
worked your way into
I was going to show you the motivating example tomorrow. But, maybe I won't get to that either. I'm not sure. It's not going very quick. Yeah. No, I mean I'm really thinking of this as being something that everybody knew, but nobody wrote it down. But it's not. I don't claim any originality here. This appeared in our paper with Brady on this, where we wrote down this example that I'll talk about. Yeah.
Other questions? Okay, so we'll give people a chance to digest all this and talk about it.
Okay, that's fine.
Okay. Okay, so I guess that means we have a break now for almost half hour. Remember, Chris Mooney's talk